Hi friends, today our topic is half adder and I will explain half adder with AOI logic and NOR or AND for both implementation of half adder. So let we start with the basic concept of half adder, that is, this is a input and output. There are two bit half adder add 2 bit A and B. So A and B, that is given here, and 0 1 0 1 double 0 double 1. Now at output we get sum and carry. This is the half adder, and half adder only add 2 bit, and that is A and B, and the output of half adder is sum and carry. So now implement or add this 2 bit A and B. So 0 plus 0, so 0 plus 0 0, carry 0, 0 plus 1, sum 1, carry 0, 1 plus 0, sum 1, carry 0, 1 plus 1 1 0 1 0 1 plus 1, and this 2 is in binary. So 1 plus 1 0, carry 1. So this is a 0 and carry 1. So it means it is 1 plus 1 2 in decimal. But when we are talking about binary, so 1 plus 1 is 1 0. It means 2 is represented by 1 0 in binary. Now check output, and output is sum and carry. So for sum, the sum is equal to, this is 1. For 0 it is not checked. For 1 it is A bar B. 0 represented by A bar, and B is, or 1 is B. So we can write sum is equal to, for this expression, A bar B. For this expression it might be A B bar, because 0 at B position. This is output that we get from sum, and that is the X OR output. So we use X OR symbol. If it is X NOR, that we use this type of symbol, but this is not. So we use this A X OR B. Now for carry, that is only one position and it is last. So we get carry A into B, and for another, that is 0, so we don't use it. Now implement it in AOI logic. So for AOI logic we get sum, so A X NOR X OR B, so that this is A and this is B, A B, and this is a symbol of A X or B, and this is sum. Now for A and B, and both are in multiplication, so A into B, and this is carry. Now how this is a representation of half adder for AOI logic. Now for and another, both are NAND or NOR. Let's start with NAND, and half adder with NAND gate. Now implement half adder in NAND gate. So we know what output of half adder, that is the sum is equal to A bar B plus AB bar. So S is equal to A bar B plus AB bar. But we want minimum operation or minimal expression, so we add some another term that you must know while you are doing a half adder for minimum expression, so that we get A bar, and so this I add this A bar, and so A bar is equal to 0, so it might not affect in this type of expression. So, and another term is B bar. These two are added, and A bar B AB bar. This is that we have already in sum output. So now take common from A, from these two expression. So we get A bar plus B bar, and B from these two expression. B A bar plus B bar. So this A. Now apply Boolean algebra rule so that we get A B whole bar plus B A B whole bar. Now applied 2 bar on this expression. It apply this 2 bar will not create any error for this minimal expression. Now solve this type of expression. We get this addition change to multiplication. B A bar A into B whole bar to it. This bar is split into 2 parts and this sign is changed so that we get this type of expression, and this is the minimum expression or minimal expression for the NAND gate in the half adder. Now same as we can do for carry, and carry is equal to A into B, that we have already know. Carry is equal to A into B, so C is equal to A into B. Now apply 2 bar and that will give a NAND gate output. So this is a simply apply 2 bar. Now draw the block diagram for this. So that block diagram or gate implement in gate. So this is A B. Now for sum A into B bar, so we use one NAND gate A into B bar, that is A into B whole bar का पूरा bar. So A into B whole bar or full bar on this expression. So we get A into B whole bar, and if I implement with this A into B whole bar with one another NAND gate, I will get A into B whole bar full bar. Now this is B A into B whole bar, or this is one another B. For this we get we use another NAND gate and we get B A into B whole bar or full bar of that expression. And for this sum expression, these two will added through NAND gate, and so we get some output, and that is A into B whole bar into B A B whole bar full bar. That is some another bar remaining here. Sorry for my mistake, but you get this sum at here. Now same as for carry, and this is A into B bar that we have already get. A into B for 1 bar, it is 2 bar, or its carry has 2 bar, so we must apply one another NAND gate. It is work as a NOT gate and negation of this bar, so we get carry output here, and that is A into B double bar. This is the minimal expression for the NAND gate in the half adder. Yeah, by this method you can get minimum expression, and that is for the minimum gate used in this type of expression, and while we are using a practical concept. Thank you. Now we will start for NOT or NOR gate, or implement NAND half adder using NOR gate. Now for half adder with NOR gate, or half adder implementation of half adder in NOR gate. So you know that sum that we have already get, that is A bar B plus AB bar. Now add some another term A bar B plus A bar plus B bar plus AB bar. These two terms are added, and it might not affect, or it will not affect on this type of expression, because A into A bar is also 0 and B into B bar is also 0. Now take common A bar from these two, that we get A plus B. Same as take B bar from this and we get A plus B. Now from this expression take these two common, so we get a plus b in bracket a bar plus b bar. Now applied 2 bar for get minimum expression of NOR gate. So I applied 2 bar, it might not affect in this type of expression that you already know. So split this type of expression a into a plus b whole bar into a bar plus b bar whole bar plus one another bar, that is this bar is remaining, that is this is this bar is remaining, and by applying the Boolean algebra rule you can split this type of expression in this way. So we get sum, and it is a minimal expression. Now same as for carry. So carry that we get is equal a into b, and now same as applied 2 bar, split that 2 bar a bar plus b bar whole bar, so that we get a minimal expression for NOR gate. Now we get this sum and carry, so we applied this concept in gate, or now make block diagram for this sum and carry. So a plus b whole bar, a b a plus b whole bar, so we use NOR gate and we get a plus b whole bar. For another a bar plus b bar whole bar, we get a bar such like this way that you know, and by this way we get b bar. Now these two will added with the help of NOR gate, and that is we get a bar plus b bar whole bar. Now these two terms we get now added through one another NOR gate, and directly we get some output, and that is this output, and a plus b whole bar plus a bar plus b bar whole bar or full bar, that we get some output by this way. Now for carry output, now this is this is carry, and that we already get, so by this we get carry at here. By this point we directly get carry, and this used in sum expression. So this is how we can implement NOR gate or half adder through NOR gate, and this is a minimal expression way. So while you are using a practical, or while you do a practical, this type of circuit might helpful for half adder to make a half adder with minimal expression or minimal gate, so it might less cheaper.